Well, hello again. Welcome back to part 2 for the chemical bonding unit. Just to recap part 1, I was trying to describe in that part of the unit how you figure out the formula, kind of like the recipe for an ionic compound. That's the case where electrons are being given away by one atom, a metal, to a different atom, a nonmetal, so that each atom can end up with a full outer energy level. Typically that's 8. For a few rare elements, that's 2. Remember the ones with only one energy level? 2 is going to be full for them. So in this next part of the unit, we're going to go into a different kind of bonding, one in which electrons are not given away or taken. And so we'll get into that. But first, I think it's good to kind of describe the 3 different types of bonding. The ionic, the one we'll deal with today, and then there's a third type, okay? We're not really going to talk much about the third type, but I will describe it here. All right, so let's start with the one that we just finished with, which is ionic bonding. Okay, again, this is where electrons are, we usually use the word transferred. Okay, and so that's from a metal atom to a non-metal atom. It's going to be important. I'm going to want you to know like which kind of atoms are involved in these kinds of bonding. So for ionic, it always has to be one of each. And there are some special cases where this isn't true. We're not getting, a super deep dive here. You'll learn more about that maybe in a chemistry class. Okay, the one we're going to deal with mostly today is called, shouldn't try to talk and write at the same time. It's called covalent. Now maybe you hear in that word the valence. Valence. Valence is the outermost energy level. Co means like together. So this is when the electrons in the outer energy level from one atom kind of overlap with the energy level, the outer energy level from another atom. So instead of the electrons actually moving, these atoms are just close enough that they can be shared by 2 different atoms. Okay, the electrons are shared by 2 different atoms at the same time. Okay, so describe it this way. Electrons are shared and this is typically between 2 non-metal atoms. So a non-metal to another non-metal. That's almost always covalent. So remember that in order to have ionic bonding, you have to have an atom that's willing to give away electrons. Well, certainly nonmetals aren't going to be willing to do that because they have so many, they're very close to having an full outer energy level. So giving away electrons just is not going to be something they're going to want to do. But sharing, I'll show you, is something that they can do. All right, and then the third type. Now, if you think about it, we figured out how a metal goes with a nonmetal, how a nonmetal goes with another nonmetal. What's the last remaining combination? That would be a metal bonded to a metal. For example, I've got my old school, like heavy steel stapler. What's holding those atoms together? Because those are all metal, typically iron. We call that, maybe not surprisingly, metallic bonding, which is between metal atoms. So no nonmetals involved here. So in this case, we're not going to transfer electrons from one atom to another. We're not going to really share them by the atoms coming closer together. It's actually a little odd, but the outer electrons are very loosely held, and so are free to move among many metal atoms. You get that written, and I'll kind of describe it maybe a little bit better. So for reasons that I'm not going to get into now, and this is something you'll do more in chemistry, you'll understand that on some metals, most metals, the electrons that are way far away from the nucleus are very loosely held. And that's because it's the nucleus that's holding the electrons in. The positive part of the nucleus, the protons, are attracting the negative electrons. There's an important idea in science that we know where positives and negatives are very attracted to each other. But it depends on how far apart they are. The farther apart they are, the more loosely held they are. So these electrons that are way out away from the nucleus are very loosely held, not as strongly attracted to that nucleus. And so they're actually free to move about. And so when you got a bunch of metal atoms near each other, those outer electrons don't really get held onto their original atom. They're free to kind of swim around. We sometimes call it a sea of electrons. And these outer electrons can just swim around freely among all the atoms that are together. It's actually what gives rise to the ability for metals to conduct electricity and heat. The motion of those outer electrons allows that electricity. That's what electricity is. It's just the motion of those electrons. Okay, there's a lot more to it than that, but that's sort of a description of metallic bonding. Okay, so with covalent bonding, now we're going to get into a little more detail. Okay, so I'm going to describe for you how to figure out how multiple atoms can bond together with covalent bonding. In chemistry class, you'll learn to figure this out yourself. But for my class, at this level, I think I just want you to recognize how it happens. Okay, so a little more detail about covalent bonding before we get into some examples. So again, just to recap, these are two or more non-metal atoms sharing valence electrons. So that all atoms have a share in 8. Now remember, like I said before, some atoms only can have 2. Atoms like hydrogen, helium, lithium, and beryllium. Those are the ones who their outer energy level will only be the first energy level it can only hold 2. Okay. So I want you to know this term. The group of atoms are called a molecule of the compound. We've heard the word compound before. That's the new substance that you get after you bond these atoms together. So in ionic bonding, we didn't really have molecules. It's just this big, usually a crystal, a whole bunch of ions just nearby each other. But with a covalently bonded compound, we're going to have a molecule, a single piece, and I'll show you what those look like. Okay. Remember, too, that the compound has completely different properties. Than the elements did. Easiest example I can give you. hydrogen. Hydrogen is a very light, clear, colorless gas. It's actually explosive. In chemistry class, you might explode some hydrogen. Oxygen, also a clear, colorless gas. I mean, those things are in the air around us. You can't see them. But what do we get when we bond two hydrogen atoms to an oxygen? We get water, the compound called water. And the compound water certainly is not explosive. It's not a gas. It has totally different properties than the hydrogen and the oxygen that make it up. So again, kind of an easy example if you think about hydrogen, oxygen, and then the compound water. All right, so as we go into our last page, I'm going to have you figure out what kind of diagrams will, what I call, work for forming covalent bonds. And this is an example of what I mean by works. I'll show you multiple examples of how some atoms could bond together. And you'll need to check for two things. First, and I've mentioned both of these, all the valence electrons in those atoms have to be shown on the diagram. Okay? So you're going to add them up and make sure they add up to the total that they should. Okay? Number two, once the electrons are moved around and shared properly, every atom must be adjacent to or must have a share in 8 outer electrons, except for those few that I mentioned that are okay with just 2. Okay? So we can have all the right electrons, but have them put in a place where some of the atoms don't have a full outer energy level. Well, that won't work. And we can have everything look like it has a full outer energy level, but maybe the electrons don't add up to what they should, and that won't work. So in every case I give you, only one of the arrangements will work. So here's 4 examples, and I'll show you how we pick out what works and what doesn't. So the fancy name for water is dihydrogen monoxide. That means 2 hydrogens with 1 oxygen. So to figure out what kind of arrangement of the 2 I gave you here will actually work, let's go through these 2 steps. First, let's account for all the valence electrons. This is where your periodic table or a good memory will be helpful. So for hydrogen, in group 1, every hydrogen should have 1 valence electron. Oxygen, over here in group 16, should have 6 outer electrons. So for 1 oxygen and 2 hydrogens, that's 6 plus 1 plus 1. That's a total of 8 electrons. So your diagram has to have 8 dots on it. Furthermore, we have to arrange those electrons so that every oxygen has 8 around it, and every hydrogen, because it's one of the special ones, has 2 around it. Okay? So let's look at our choices here. We see 8 dots. That's the number that's right for an oxygen and 2 hydrogens. We see that around each hydrogen, there are 2. You see the 2 here, and the 2 here are adjacent to the hydrogens. That's good for the hydrogens. They're happy that way. And the oxygen needs 8. It has 8 around it. Okay? So this is a good diagram. What's wrong with this one? You'll notice it has 8. 1, 2, 3, 4, 5, 6, 7, 8, but they're not placed in the right location. So this hydrogen is happy. It's got 2, 1 on each side. This hydrogen is happy. It's got 2 on each side, and we're looking good. But the oxygen is not. The oxygen does not have 8 around it. It only has 6 around it. So that is not going to work. Okay? Now, let's look at carbon dioxide. Another clear gas, odorless. So let's add up the electrons. Again, add them up. 1 carbon in group 14 on your periodic table, so that's 4 for it. And then as I mentioned a moment ago, each oxygen should have 6 around it. So the math is 4 plus 6 plus 6. That's a total of 16 outer electrons. It's good to kind of show your work there when you do that. So whatever diagram you pick, it better have 16. And because we're not dealing with any of our special, really small atoms, we're going to have 8 around each one. So let's add these up here. We have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's good. And in this one down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Both have the right number of electrons. But they're not arranged the same, are they? Which one of those has the arrangement of those 16 electrons so that every atom can see 8 around it? Not this one. This carbon only has 4 around it. Not going to work. The oxygens only have 7 around it. Not going to work. But down here, look what we do. We actually put these oxygen electrons here, these two, adjacent to the carbon, and carbon puts 2 of its electrons adjacent to the oxygen so that both of them can claim a share in those 4. So now this oxygen, 1, 2, 3, 4, 5, 6, 7, 8, kind of maybe circle it here so you can see the 8 that oxygen can claim. This oxygen similarly can claim 8, and the carbon, 4 on each side, it has 8. So that is a good arrangement that will work. Okay. In chemistry class, again, you'll learn a little bit more about this. This is a real strong bond. We call it a double bond because there's 2 pairs on each side of the carbon that are being shared. Okay. All right. Why don't you try this? I'm going to pause the video here for a minute, or you can pause the video and check out the nitrogen tribromide and the oxygen gas. That's 2 atoms of oxygen bonded to each other. See if you can figure out which of the arrangements in each case actually works, okay? Then restart the video, and I'll kind of give you the answers, all right? Try it on your own first. Okay, so let's start with the nitrogen tribromide. We add up our outer electrons first. So nitrogen in group 15, it should have 5. And then 3 bromines. Now a bromine is over here in group 17, so they'll each have 7. So that's 7, 7, and 7. That's 21. 21 plus 5. We're looking for a total of 26 electrons. Okay, so did you find the one with 26? And did we arrange those electrons so that everything has a share in 8? All right. I can see right off the bat that the bromines all look happy here. The nitrogen looks happy. I see 8 around it. Actually, no, I see 10 around that nitrogen. 10 is too many. Again, special cases you'll learn about in chemistry, but not in here. So that's not going to work. Here we have 8 around the nitrogen. I see 8 around the bromine. Each one. Now it sounds like we should have 32, right? But that's not quite right because some of these are being counted twice. So there are actually 26 there. So this second diagram is the correct one. And then with oxygen gas, with oxygen having 6 outer electrons, we should have 6 plus 6, or a total of 12 dots. Okay, let's add these up. I see 8, 9, 10, 11, 12, 13, 14. Well, that doesn't work. You can't make up new electrons. You have to have 12 electrons so that each oxygen is adjacent to 8 of them. So here are 12 electrons. We've got us, again, like we had with the carbon dioxide, we're sharing 2 pairs between them. And so that will work because everything has 8. All right? So there's an example of what that looks like. If you need to go back and play this again, by all means do. Maybe just the parts that you need to hear again. Hopefully you watched this with the video playing so you didn't try to shortcut it, because I'm not sure it's going to sink into the brain as well if you're just looking at the captions or writing what you see me write on the screen. Okay? All right, we'll give you some practice with this. Hopefully it'll go well. Thanks for watching.